magnetic dipole in uniform magnetic field. Let us see if a magnetic dipole is suspended in an external uniform magnetic field. We have considered a magnetic needle which acts as a magnetic dipole. This magnetic dipole is suspended from a rigid support. It is placed in an external uniform magnetic field B. We know the dipole experiences a torque and hence it oscillates. Now, due to the external magnetic field B, if the dipole deflects through an angle theta, we know the deflecting torque 2D equal to mb sin theta. Or if theta is negligible, small angle oscillation, if theta is approximately equal to 0, deflecting torque equal to mb into theta. Let us consider this as an equation number 1. Now, if alpha is the angular acceleration and I is the moment of inertia of the magnetic dipole, restoring torque tau r equal to I alpha, or tau r equal to I d square theta by dt square, which is the equation number 2. But at equilibrium, deflecting torque must be equal to restoring torque. That is I d square theta by dt square, which is restoring torque, that equal to mb theta, which is the deflecting torque. This happens only at equilibrium. That is when the dipole comes to rest. Or this we can write d square theta by dt square equal to mb by I into theta. We know this is the equation for simple harmonic motion. From this, so we put a negative sign also. Here we have written only the magnitude. So in the place of omega square, we know mb divided by I, or omega equal to root of mb by I. Now let us see what is the frequency of oscillation. We know the equation T equal to 2 pi by omega, or that is equal to 2 pi into root of I by mb. Hence, frequency of oscillation is 1 by time period, which is equal to 1 by 2 pi into under root mb by I. Magnetic potential energy. If tau is the torque experienced by the dipole in the above case, and theta is the angle turned by it in uniform magnetic field, capital B, then potential energy is integration of tau d theta, which is integration of mb sin theta into d theta, that is minus mb cos theta. Or we can write potential energy is equal to minus m dot b. Now let us see some special cases. When theta equal to 0, potential energy is minus mb cos 0. We know cos 0 is 1, so potential energy is minus mb. When theta equal to 90 degree, That is when the dipole is perpendicular to the external magnetic field. Then potential energy is minus mb cos 90, which is equal to 0. When theta is 180 degree, when the magnetic moment is anti-parallel to the external magnetic field, potential energy is minus mb cos 180, which is equal to plus mb. Or we can say, when theta is 0, m is parallel to b, the dipole is in most stable position. And when theta is 180 degree, m is anti-parallel to b, or the dipole is in most unstable position. Thank you.